Hello students, welcome to EPG Pathshala. I am Vinodini Kapoor from Chandigarh and I am teaching in the Faculty of Management. Today we are going to study about the module Optimization Analysis. This is under the paper Management Information Systems. After completing this module, students will be in a position to understand what is the basic concept of optimization. They shall understand the various components that form the optimization function, list the various complicating factors in optimization, understand the importance of optimization, analyze the optimization modeling process, and discuss what are classifications of the optimization model. Let's come to the concept of optimization. It is, in the simplest of the terms, referring to the task of finding an alternative with the most cost-effective or highest achievable performance under a given set of constraints. This is achieved by maximizing the desired factors and minimizing the undesired ones. To simplify further, maximization implies to attain the highest or maximum result without regard to its underlying cost or expense. Practice of optimization is restricted by the lack of full information and lack of time to evaluate what information is available. Decision support systems are very useful in analytical modeling. The four basic types of analytical modeling supported by the decision support systems are: firstly, the what-if analysis; secondly, the goal-seek analysis; thirdly, sensitivity analysis; and lastly, optimization analysis. Hence, optimization analysis is a technique to find the optimum value of a target variable under given circumstances. Here, the target is not fixed. Rather, the target needs to be arrived at after taking into consideration constraints involved in achieving the targets. In this analysis, one or more variables are changed after taking the constraint into account until the best alternative or the optimal value is found. This method is widely used for making decisions related to optimum utilization of resources in an organization. During optimization analysis, the values for one or more variables are repeatedly changed, keeping in mind the specific constraint until the best possible values of the target variable are found. To exemplify, one can determine the highest level of production that can be achieved by varying job assignments to workers in terms of, say, man-hours, keeping in mind that the same workers are skilled and their job assignment cannot be changed. Optimization analysis would require special purpose software and techniques such as linear programming. For instance, optimization analysis is used in finding out optimum amount of promotions that could be used with the given constraint of budget, the use of print media. Now, Solver, a what-if analysis tool in MS Excel, is used for conducting this optimization analysis. Without the right information available to the right people at the right time, an organization cannot make the right decision, nor it can take the right action, nor it can complete effectively and prosper. Information must be crafted and made available to employees, customers, suppliers, partners, and consumers in the form they want it the moment they must have it. Extracting information from data and then optimizing the information in this particular manner is very essential for business success. Components of optimization. The purpose of optimization is to develop the optimal solution to a problem given a set of restrictions and assumptions. The three components of optimization are: firstly, the decision variable. They usually measure the amount of resources used, such as money to be allocated, to some purpose, or the level of various activities to be performed, such as the number of products to be manufactured. For example, in a scenario of shipping products from 3 different plants to 5 different warehouses, as shown in the network image, there are 3 into 5, that is 15 different paths along which products could be shipped. So, there shall be 15 decision variables, each one representing the amount of product shipped from a particular plant to a particular warehouse. Further, if each plant produces 4 different product types, to determine the optimal shipping plan in each of the next 6 months shall lead to 360 decision variables. This is a multiplicative factor of 4 different product types, 3 different plants, and 5 different warehouses. This simple example illustrates how a model can become large rather quickly. So, part of the art of modeling is deciding how much detail is really required in a given situation. Once the decision variable is defined, the next step is to define the objective and outline the constraints. Second, the constraint. Constraints are logical conditions that a solution to an optimization problem must satisfy. They reflect limiting conditions to real world situations such as resource allocation, budgets, production capacity, market demand, available funds, etc. To define a constraint, it is essential to compute the value of interest using the decision variables. The next step involves to assign an appropriate limit, such as the less than equal to, the equality, or the greater than equal to this computed value. A constraint can directly be placed on a decision variable. Policy constraints are determined as per organization policies. To exemplify, in a situation of modeling of consignments shipped in and out of a warehouse over time, one needs a balance constraint to specify that in each time period, the beginning inventory adds up to the products received and subtracting the products shipped equals to the ending inventory. And of course, the ending inventory in one period becomes the beginning inventory for the next period. Integer constraints. Optimization software allows to specify constraints requiring decision variables to assume only integer, that is, whole number values in the final solution. To exemplify again, while scheduling a fleet of trucks, a solution that calls for a fraction of a truck to travel a certain route would not be useful. Integer constraints can be applied only to decision variables, not to quantities calculated from them. Objective function. It is representative of the main aim of the model. The goal is to minimize or maximize the mathematical function based on the decision variable under a set of constraints. This is achieved through linear programming. Linear programming is a mathematical method for determining the way to achieve the best outcome, such as
maximum profit, or lowest cost in a given mathematical model for some requirements represented as linear equations. The statement of an optimization problem is stated as to find x for certain values of x that may range from 1 to say n, which minimizes the function fx is subject to constraints such as g as a function of x for numerous values that range from 1 to say m, and L as a function of x that may equate to 0 for different values of j, where x is an n-dimensional vector called the design vector, fx is called the objective function, and g and L are known as inequality and equality constraints respectively.
Okay, now let's come to what are the complicating factors in optimization. Several factors can make optimization problems fairly complex and difficult to solve. First and foremost, existence of multiple decision variables in a particular problem. In firms with single product, calculating the profit maximization output level is much easier than firms that have multiple product lines, and the impact of each product is to be considered. The complex nature of the relationship between the decision variables and the associated outcome. Examples of the government policy decisions on opening of zero balance accounts. It may become difficult to derive a direct relationship between the enrollment and the impact on deposit due to availability of the biometric machines, the awareness among the localites, and the readiness of the people to join. The possible existence of one or more complex constraints on a particular decision variable. Virtually every organization has constraints imposed on its decision variables by certain budget allocation on capital, on labor, resources, infrastructure over which it can exercise control. These constraints must be incorporated into the decision problem, else the optimization technique that is applied to the problem may yield a solution which is unacceptable practically. The presence of uncertainty or risk. This is easier when there is a limit to analyze the decision making under certainty. That is, problems in which each action is known to lead to a specific outcome. For example, virtually every organization has constraints imposed on its decision variable by the limited resources of capital, personnel, facilities over which they have control. These constraints must be incorporated into the decision problem. For example, we wish to design the fuel-efficient, high-mileage bike. Now our objective may be to maximize the engine efficiency. The engine may be required to provide a specific power output with an upper limit on the amount of engine emission. Certain parameters such as the ignition ability, quick acceleration, the oversize, and the wider tire will serve as a constraint for optimization. The design variables that are allowed to be changed during the optimization may be the compression ratio, the fuel mixture ratio, etc. The concept of optimization is not merely limited to the engineering problems only. It's also possible to optimize the financial portfolio of an organization, optimize the revenue and expenditures of a company, optimize route of a delivery truck, optimize the advertising budget, the sales force, etc.
Let's come to the point that why is optimization necessary? Optimization is the act of achieving the best possible result under given limiting factors. Its applications can be seen in multifaceted disciplines such as design, construction, maintenance, etc., where engineers have to take decisions. The goal of all such decisions is either to minimize effort or to maximize benefit. This is evident from the basic principle that every business operates with the underlying objective of profit maximization and resource minimization. The effort or the benefit can be usually expressed as a function of certain design variables. Hence, optimization is the process of finding the conditions that give the maximum or the minimum value of a function. Optimization, in the broadest sense, can be applied to solve any engineering problems. For example, design of aircraft for maximum weight, optimum, minimum time trajectories for space missions, optimal design of electric networks, optimal production planning, resource allocation, scheduling, shortest route, minimum processing time in production systems. The various benefits of optimization can be summarized as cost reduction, safety and error reduction, innovation and efficiency, reproducibility, and time saving. The necessity and importance of optimization can be observed since it helps to find the answer that yields the best result, that is, the one that attains the highest profit, output, or happiness, or the one that achieves the lowest cost, waste, or discomfort. Often these problems involve making the most efficient use of resources, including money, time, machinery, staff, inventory, and many more. Optimization techniques are a powerful set of tools that are important in efficiently managing an enterprise resources and thereby maximizing shareholder wealth. A number of factors that we have stated make optimization analysis a key tool in mathematical programming. First and foremost, cost reduction, automation of processes, and proactive planning at each step of processes not only removes duplication of time and effort, but also removes redundancies that may be present. Re-engineering products as per changing business and customer needs lead to optimization, thus removing and reducing unnecessary expenditure. Safety and error reduction. Management best practices and quality management ensures process to be mitigated with parameters that ensure quality with minimal defects and correction at each step. This promises safety as per international standards and error reduction. Time efficiency. Removal of redundancies and effective planning is an essential step in better management of time. Reproducibility. Documenting procedures and archiving essential steps in the development and production cycle ensures the knowledge behind is not lost. Also, as experts move from organizations, their intelligence and competence can be utilized by organizations by ensuring effective product and service documentation. Optimization at this level ensures reproducibility and rebuilding to be a less time consuming activity from a business standpoint. Innovation and efficiency. Optimization is the diligent method of ensuring business effectiveness in terms of resource employed and the final outcome. These efforts help organizations achieve competent outcomes and high return on investments while delivering their mission in unprecedented business climates.
Now let's discuss the optimization modeling process. Optimization modeling requires appropriate time. The general procedure that can be used in the process cycle of modeling is to primarily describe the problem and then prescribe the solution. It is required to control the problem by assessing, updating the optimal solution continuously, while changing parameters and structure the problem. Clearly, there is always feedback loops among the general steps. Firstly, the mathematical formulation of the problem. Now, as soon as the problem is detected, a proper understanding is imperative in order to adequately describe the problem in writing. Developing a mathematical model or a framework facilitates to devise or use an optimization solution algorithm. The problem formulation must be validated before it enters the next stage. A good mathematical formulation for optimization must be both inclusive of the problem situation and exclusive of what does not belong to the problem. Finding the optimal solution. Now, this is an identification of a solution algorithm and its implementation stage. The only good plan is an implemented plan which stays implemented. Thirdly, managerial interpretations of the optimal solution. Now, once the algorithm is drafted and the appropriate module of the software to apply is decided, to utilize software to obtain the optimal strategy. The solution should be presented to the decision maker in the same style and language used by the decision maker. This means we are providing managerial interpretation of the strategic solution in the simplest of the terms.
Post-solution analysis. These activities include updating the optimal solution in order to control the problem. It is crucial to periodically update the optimal solution to any given optimization problem. A model that was valid may lose validity due to changing conditions, thus becoming an inaccurate representation of reality and adversely affecting the ability of the decision maker to make good decisions. The optimization model should be versatile to be able to adapt to changing business needs. The importance of feedback and control. It is necessary to emphasize on the importance of feedback and control aspects of an optimization problem. The very nature of the optimal strategies environment is changing, and therefore, feedback and control are an important part of the optimization modeling process. Now we'll discuss the classification of the optimization model. An important step in the optimization process is classifying your optimization model, since the algorithms for solving optimization problems are tailored to a particular type of problem. The first classification is continuous optimization versus discrete optimization. Some models only make sense if the variables take on values from a discrete set of integers, whereas other models contain variables that can only take on any real values. Models with discrete variables are discrete optimization problems. Models with continuous variables are continuous optimization problems. These tend to be easier to solve than the discrete optimization problems, as the corresponding objective function and the constraint at a certain point can be used to deduce information about points in its neighborhood. Continuous optimization algorithms are important in discrete optimization because many discrete optimization algorithms generate a sequence of continuous subproblems. The second classification is unconstrained optimization versus constrained optimization. An important aspect of classification is between problems in which there are no constraints on the variables and those with constraints on the variables. Unconstrained optimization problems arise directly in many practical applications in which the constraints are replaced by a penalty term in the objective function. Constraint optimization problems arise from applications in which there are explicit constraints on the variables. The constraints on the variables span from limiting factors to systems of equalities and inequalities that model complex relationships among the variables. Constraint optimization problems can be further classified according to the nature of the constraint, such as they could be linear, nonlinear, convex, and the smoothness of the function being a differentiable or a non-differentiable one. The third classification can be none, one or many objectives. Most optimization problems have a single objective function. However, there can be exceptional cases when optimization problems have no objective function or multiple objective functions. Complementarily, problems are pervasive in engineering and economics. The goal is to find a solution that satisfies the complementary condition. Multi-objective optimization problems arise in many fields, such as engineering, economics, and logistics, when optimal decisions need to be taken in the presence of two or more conflicting objectives. In practice, problems with multiple objectives often are reformulated as single objective problems by either forming a weighted combination of different objectives or by replacing some of the objectives by constraints. The fourth classification refers to deterministic optimization versus stochastic optimization. In deterministic optimization, it is assumed that the data for a given problem are known accurately. However, for certain actual problems, the data cannot be known accurately for a variety of reasons, such as simple measurement error. The second reason is that some data represent information about the future, such as product demand or price for a future time period, and simply cannot be known with certainty. In optimization, under uncertainty, termed as stochastic optimization, the uncertainty is incorporated into the model itself. Robust optimization techniques can be used when the goal is to find a solution that is feasible for all data and optimal in some sense. Stochastic programming models take advantage of the fact that probability distribution governing the data are known or can be estimated. The goal is to find some policy that is feasible for all the possible data instances and optimizes the expected performance of the model.
Okay, students, now let us summarize what we have learned in the module. Optimization techniques are very crucial activities in the managerial decision-making process. According to objective of the firm, a manager tries to make the most effective decision out of all the alternatives available. Optimization analysis is a process through which a firm estimates or determines the output level and maximizes its total profits. Now, those who manage and control systems of men, machines, markets, and money face the continuing problem of improving, or rather, optimizing business performance. Any project in the organizational climate is itself a system which comprise a network of elements or tasks that are interconnected and interdependent, that work together to achieve a precise goal. In fact, that the tasks are carried out by a pool of finite resources mean that optimizing the sequence of tasks is a matter of considerable complexity. The problem may either be of reducing the cost of operation while maintaining an acceptable level of service and profit of the current operations, or providing a higher level of service without increasing cost, maintaining a profitable operation while meeting imposed government regulations, or improving one aspect of product quality without reducing quality in another. To identify methods for improving the system operation, one must construct a representation of the model of the physical system, which could be to describe the effect of a variety of proposed solutions. Mathematical optimization is that particular branch of computational science that seeks to answer that particular question. What is the best for problems in which the quality of any answer can be expressed as a numerical value? Now, such problems arise in all areas of business, physical, chemical, and biological sciences pertaining to engineering, architecture, economics, management, and so forth. Thank you.